Ahoy! Great to see everybody. So it's my pleasure to welcome this week's seminar speaker, Sebastian Will. I've known Sebastian, I realized, since about 2005, when he was, I guess you spent a year in Wolfgang's group, just down the hall. Monica and I were in Blotton's group. Blotton's group was the straight lace folks. Wolfgang's group is now pretty straight lace, but back in those days, the place was just absolutely out of control. We sort of went into total party animals. So you can
John, what's your group now? Like, how would you compare now?
Me? Oh, super low key by comparison.
Oh,
They, you know what? I think we just leave it at that. Yeah. So after that year with Wolfgang, Sebastian did his diploma research working on atom optics and sodium in Mainz, and finished his undergraduate work there before joining Emmanuel's law group and really conducting a number of the seminal experiments exploring the dynamics of ultra-cold atoms and optical lattices, and sort of cementing this as an exciting platform for antibody physics. For his postdoc, he made a pretty bold choice to go in, some might say a bad choice, to go into molecules. Historically, that was a pretty scary direction to move in. The rule of thumb when I was a student was molecule experiments just ate doctoral careers, and it was hard because they're just so hard. They have so many transitions.
they have one too many atoms.
Yeah. My view is any atoms is too many atoms. I just like photons, but anyway.
That's beautiful.
Exactly. So anyway, he made the bold choice to go into molecules, and I think taste is really important. He picked the right time to do that, and worked with Martin Zwierlein studying sodium-potassium molecules at MIT before starting his own group at Columbia in 2016. And I have to say, since then, it's just really absolutely taken off in leading that field and turning these sodium-cesium molecules into just an absolutely amazing platform. They're studying many body physics. There are lots of results along the way, culminating in this recent breakthrough demonstration of a quantum degenerate gas of bosonic molecules, which I guess is what we're going to hear about today. As someone who prefers photons, certainly to people, but probably also to atoms, present company accepted. You guys are better than me. But I mean, as someone who prefers photons to atoms, I've also been fascinated to see that Sebastian has another effort developing meta optics and integrating them with atoms. So if you're a photonics person, I see a couple of you already opening up your laptops to think about photons instead of atoms, which is understandable, as I said, but you might want to chat later with Sebastian about these ideas for integrating metasurfaces with atom arrays, which seems like we're saying. So with no further ado, Sebastian, please take it.
Yeah, thanks so much, John. I mean, it's almost impossible to give the talk after this introduction. It was stunning. Also going down on history lane. Really, I mean, I'm really thankful for the invite to come here. Actually, a dream comes true today. It's my first time at Stanford University.
Really?
Yeah, and still at the same time, it feels a bit like coming back to a place that is very familiar. People I know for a very long time, John, Monica for 20 years, and of course I know for almost as long, and others actually in the room.
Who's your favorite?
Sorry, it's a holy trinity. So it's really fantastic to be here. And on the comment about going into molecules at MIT during my postdoc, Yeah, it was crazy, but I think the reason why we did it was we knew so little about molecules that we weren't even scared of it. And then it took us a couple of years to actually make progress. But if we had known how difficult it is, we would have never done it. Anyhow, but today I'm really excited to tell you about our work on creating and exploring Bose-Einstein condensates of dipolar molecules. Hopefully also a little bit about the second effort that John mentioned. We have time. So yeah, since molecules are so complicated, people often ask me, why do you actually work on molecules? Are molecules too complicated? And sometimes I give, fancy answer, talk about quantum simulation and quantum computing. But in some sense, what truly excites me is something simpler than that. I mean, if you look back sort of in the last 100 years, concurrently with the theoretical development of quantum mechanics, there's a really experimental effort to bring more and more complex quantum systems under full control, starting with spins, electrons, protons, atomic ions, nuclear atoms. And in some sense, molecules are a new frontier in terms of complexity. And I'm just curious to see what will be possible when we bring these molecules under control, because if you think about it, at each of these steps of bringing new systems under control, we have new opportunities for science and actually also for technology. So it will be interesting to see. Let me be a little bit more precise what I mean with quantum control. So when I talk about quantum control, there are a few aspects to it. We can think of an ensemble of individual quantum systems. Can be, spins, atoms, molecules, qubits, whatever. One aspect of it is that, of course, you would like to be able to prepare an ensemble with each quantum system in a defined state, initialized system, perhaps with all initialized ensemble with all systems in the ground state. Another aspect is that we would like to be able to control, induce control changes of the quantum state using lasers or microwaves, bring all elements to an excited state. And the third aspect is that we would like to be able to engineer interactions between the quantum systems in a way that we can create correlations and entanglement. One aspect that makes it challenging to actually achieve that in practice can be that the system is too hot, and then you get thermal excitations. So cooling down the system will help to keep the system initialized in the desired state. So you want to cool it below the lowest excitation energy in your system. So that's sort of more general comment. But if we assume that our ensemble here is perhaps a gas of atoms or molecules, or also electrons, other things may happen when we cool this ensemble down. So we can think of this ensemble as a billiard balls, if you wish, at a certain density, and the interparticle distance is the density to the power of -1/3. That's sort of a classical picture, but if you look closely, we assign wave packets to each particle, and the extent of the wave packet corresponds to the thermal de Broglie wavelengths, which is proportional to the square root of the temperature. So when we cool down the ensemble, actually the extent of the wave function of each particle increases. And if it increases further, well, something interesting happens. The wave function of a thing that describes the location of a single particle starts overlapping with a neighbor. So that's the point that we call quantum degeneracy. And here we need to distinguish quantum statistics. For fermions, they obey the Pauli principle, and the particles like to minimize overlap. So basically, n fermions avoid each other. For bosons, basically the opposite happens. All bosons tend to accumulate in one shared macroscopic quantum state. And keep in mind that's for an ensemble of identical quantum particles, so the internal state is controlled. And by going into a Bose-Einstein condensate, you're also controlling the state of motion. N bosons are all sharing the same motional wave function, which means you're also controlling the motional state. Let's look a little bit closer into this criterion of quantum degeneracy. So I told you something interesting happens when the position uncertainty, the thermal de Broglie wavelengths, is on the scale of the interparticle spacing. We can write down this in the form of the equation. And we can reshuffle this a little bit around, and then we see then we can determine the temperature at which degeneracy happens as a function of the density our ensemble. The degeneracy temperature depends on the density to the power of 2/3 in the case of a 3D gas. So basically, when I have a high density ensemble, the degeneracy temperature is high, and when the density is low, the degeneracy temperature is also low. So that actually plays a role all across quantum systems in nature. For extremely high density systems like a neutron star, the degeneracy temperature is absurdly high, so even though neutron stars are pretty hot, they're actually degenerate quantum matter. For electrons in a metal, the density is lower than the neutron star, but still relatively high, so the degeneracy temperature is in thousands of Kelvin. However, the gases, quantum gases that we are working with, are typically at very low densities. So in some sense, it's a bit crazy that when people want to go to a regime of quantum degeneracy, for the typical densities we work at, the degeneracy temperature is sub-microkelvin temperature. And so it's actually quite a bit crazy to pursue this, but we do it because we really stand on the shoulders of giants who have developed all the tools to make it possible. And the key breakthrough here was to observe Bose-Einstein condensation of atoms. In the mid-90s, it was observed that you can cool down atoms to sub-microkelvin temperatures, and they then go into the Bose-Einstein condensed state. All atoms share the exact same internal state and the exact same state of motion. And that really kicked off a wave of developments, as you know, and in some sense opened the door to atomic quantum simulators, ultra-precise clocks, and in the aftermath, all these developments also atomic systems as a very strong contender. So that's sort of on the atomic side of things. What about molecules? It's actually interesting to note, how this field of quantum control started. So perhaps we can say it started with the work of Ayarabi at Columbia in the 30s of the last century, where he actually used the oscillating magnetic field to spin the nuclear spin of lithium. And interestingly, he didn't do that experiment with atomic lithium, but using lithium fluoride and lithium fluoride molecules. So the idea to control quantum states in molecules is actually not so new. But it basically took 100 years to get full quantum control of molecules. So why is that? Well, the molecules are a lot more complicated than just the nuclear spin. So here I showed you molecular potential. This is the energy axis. This is the distance between two atoms in a diatomic molecules. And then you have here interaction potential. In that potential, you live vibrational states. So these are the lines here. So this is quantized vibrational motion of the atom, typically with energy gaps on the terahertz scale. Then on top of that is a substructure of molecular rotation, typically with energy gaps between the states on the gigahertz scale. And then on top of that, there's hyperfine structure. So that is what makes molecules challenging. You really want to prepare molecules in a perfectly well-defined quantum state. In particular, we are interested in preparing molecules in the low vibrational ground state, in the eternal ground state, because that is where they cannot decay on the one particle level to lower lying states. So we can expect stability on the one particle. I also just saw a diatomic molecule on the steering quad. A classic one. So on the theory end, it was understood early on, more than 2 decades ago already, that it would be really interesting to bring ensembles of molecules under full quantum control. Proposals range from realizing novel many-body quantum systems, simulation of quantum magnetism, studies of quantum chemistry, precision measurements, and quantum computing. Interestingly, that was one of the first proposals by David Bell that really drove the field forward in terms of inspiring to actually do that. It was also understood that it would be of particular interest to study dipolar molecules. So let's quickly remind ourselves what dipoles are, how they interact. We have two dipoles. We assume the dipoles to be aligned on the vertical axis. They interact such that the interaction energy falls off as 1 over the distance cubed. And there's an anisotropy that is such that when two dipoles meet side by side, they repel each other, and when they meet head to tail, they attract each other. So This interaction has a long-range character, especially in contrast to the contact interactions that are typical in ultra-cold atomic gases. Such interactions are ideal to create strongly interacting highly entangled quantum states, at least from the theoretical. So how do molecules, compare to other dipolar systems that we know in atomic physics? Of course, there's magnetic atoms with a lot of beautiful experiments and pioneering work by Ben on many quantum physics with magnetic atoms. Compared to magnetic atoms, the dipole of molecules is quite a bit stronger. But on the other hand, the dipole of molecules is quite a bit weaker than the dipole-dipole interactions of Rydberg atoms. However, somehow the molecules lie in a very interesting spot where you can hope to tune from weak interactions to strong interactions. And on the many-body level, that's really where you hope to see interesting quantum phases to occur. So it will be interesting to see what we can do. So the field of ultra-cold molecules was kicked off with amazing work by the legendary David Jin and Junier at Gila in 2008, where they showed for the first time that you can actually assemble ultra-cold KRB molecules from ultra-cold clouds of potassium and rubidium. And with their work, they already were able to go to microkelvin temperatures. And KRB is a dipolar molecule. And this work inspired a number of groups around the world. By now, there's about a dozen groups worldwide that can assemble ultra-cold dipolar molecules like that. But it turned out already very early on in Debbie's and June's experiment that, and also in all other groups, that ultra-cold molecules undergo very strong inelastic two-body collisions. So strong that basically any two-body collision of molecules leads to a loss, universal two-body loss. And that meant, although the molecular gases were here already at a microkelvin temperature, which was just above degeneracy, it was basically impossible to cool down further to degeneracy, because that would require evaporative cooling. And evaporative cooling requires collisions. And if collisions are so inelastic that every single collision leads to a loss, you cannot cool. So that seemed to be like an insurmountable problem. It hasn't held back people from doing interesting things. So people started studying spin exchange physics and lattices. Turned out nuclear spin states and also rotational states in molecules showed very long coherence time. Also, it became possible to study quantum chemistry with quantum state controlled reactants. And actually, June also managed to generate a degenerate Fermi gas by leveraging favorable quantum statistics in their mixture, which was amazing that it was possible, but they couldn't really do a lot with it because the losses still persisted in this Fermi. However, just a few years ago, it turned out that the situation of these devastating inelastic losses may actually change. There were very interesting experiments on collisional shielding methods. June studied resonance shielding. John Doyle demonstrated microwave shielding, and microwave shielding was also used in Manuel Bloch's group with fermionic NEK molecules. And in these efforts, it was actually demonstrated that using static E fields or rotating microwave fields, you could actually engineer balloons between molecules such that you can suppress losses, inelastic losses, by about a factor of 10. So for fermionic molecules, that was actually enough to allow evaporative cooling into a degenerate Fermi gas. So the side note here is that for fermions, due to the Pauli principle, these inelastic loss rates were actually already substantially suppressed, because in the collision process, molecules have to tunnel through a P-wave barrier. So a factor of 10 improvement was enough to allow evaporative cooling. But obvious question, what about bosonic molecules? In practice, losses in bosonic molecules are 100 times higher with the absence of the P-wave barrier. So basically, if you were to hope to cool bosonic molecules to degeneracy to Bose-Einstein condensate, you would have to reduce losses by a factor of 100 to 1,000. The big question is, was at the time, is this possible? So that's why our experiment comes in. We work with sodium-cesium molecules. The main reason to pick this molecule initially is the large dipole moment of 4.65. So just for comparison, the most famous dipolar molecule is probably water, and has a dipole moment of 1.8. So really strong dipole properties. Yes. And we can tune it effectively in the lab frame using electric, static, and oscillating electric fields. And with this large dipole moment, you can tune the characteristic lengths of these interactions, the dipolar lengths, to lengths of up to 10, several tens of micrometers. And that already shows you, when you compare it to the typical intermolecular spacing in our samples on the micrometer scale, that you should be able to drive the system to strong interaction. The characteristic length scales interactions a lot larger than the space, or can be a lot larger. Okay, so with that, let's get into the creating the part of the talk. So that's an effort that has started a few years ago at Columbia University, and there's a lot of steps that led to where we are today. And I will try to give you a brief summary of what. So all of this started in an empty lab in 2018. So laser system to laser cooling of sodium-cesium in the vacuum chamber in which all of this happens. And then the first step was actually to create overlapping ultra-cold mixtures of sodium and cesium and cool them down to degeneracy. So that was actually still quite an adventure, because sodium and cesium was the last alkali mixture that had to be cooled. It was not studied at all. So it wasn't clear how the scattering properties are and all that. But lo and behold, it was possible to make overlapping species of sodium and cesium. And it even turned out that these atomic species are miscible, which is actually quite fantastic. You get truly overlapping clouds. It's not easy with most other alkalis. Then we use a Feshbach resonance to associate pairs of sodium and cesium atoms into a weakly bound molecule. The Feshbach resonance in our state is in our case, at 864 Gauss. So initially, we cool the mixture at 900 Gauss, and then we ramp the field rather quickly across this Feshbach resonance. And that makes us about 50,000 weakly bound Feshbach molecules. Some molecules essentially the highest vibrational state. We call this, cartoonish molecular potential that I drew for you. So now we have molecules in the highest vibrational state. We want to go to the low vibrational ground state that we do with a 2-photon coherent laser transfer scheme, stirrup scheme that brings the molecule from the Feshbach state to the low vibrational ground state. We can do this transfer with an efficiency of up to 90%, going to the ground state and also come back and associate the molecule into atoms where we usually detect gas. So what have we achieved so far? So this is, of course, it's like 3 years of work summarized in 2 seconds. So what have we achieved so far? We have made a gas of 10,000s of sodium-cesium molecules in the low vibrational ground state. All molecules are in the exact same internal state. So we have internal quantum state control. Coming from the atom side of things, that seems completely trivial, but for molecules, that's not totally trivial. Anyway, so that is sort of the backdrop on which you're working. Now we want to also control the motion. But here, an important element is microwave. So what does that mean? Well, initially we create molecules in the low vibrational ground state, so also in the rotational ground state. So rotational quantum number J equals 0. And then we have microwave transition to the first rotation silent state J equals 1. And we basically have 3 possible transitions, sigma plus, pi, and sigma minus microwave transition at a frequency of around 3.5 gigahertz. Turns out in NACS, these excited states are very close by to each other. So in order to separate them, it was already early on clear to us, we need to be able to make very clean microwave polarization. So for that, we actually developed a new type of antenna. We call it a Brookhaven antenna. It's a microwave antenna that's built out of 4 loops that can be individually controlled in terms of the pace of the microwave field and the power of the field that feed to it. It's very thin, it's millimeter thin, basically. It's like 5 centimeters across or so. With that, we can make extremely clean circularly polarized microwave fields to address our molecules. Luticity that we can measure spectroscopically is like on the order of 2 degrees. Believe we can even a lot better by now. I can talk about that more later. But basically, this antenna is brought up to the viewport of our vacuum chip. Then molecules are. So when we use this antenna and drive our microwave rotational transitions, we can flip between sigma plus and sigma minus. And first thing is to study Rabi flooding. And actually, to our surprise, we saw really nice and strong coupling, 40 megahertz Rabi frequencies. So that's pretty cool. So, since people started for a long time about using molecules for quantum computing, if you think of it as like other markers, you can do it in 6 nanoseconds. At the same time, rotation coherence times with molecules were just shown in Simon Cornish's lab to be as long as 60 seconds. So it means you can basically run 10 billion gates, single qubit gates. It's pretty cool. But we are not into quantum computing in my lab, so let's move on to group. So that brings us to microwave shielding of sodium-cesium. So what do we do here? Here we don't drive the system resonantly, but with a blue detuned sigma plus microwave. And if we do things right, we can prepare a dress state, the plus dress states, which mixes the rotation ground state 0, 0, and the first rotation excited state 1, 1. And the mixing angle, how much the excited state is mixed, is determined by this angle phi, which depends on the ratio of tuning and the Rabi frequency of the dressing. So that's interesting. So an important side note is that this dress state is a superposition of opposite parity states. 0, 0 and 1, 1 have opposite parity, which means that is a means to induce a dipole moment. When we initially prepare the molecule in the 0, 0 state, there's no dipole moment in the lab frame. Something very counterintuitive. It's a dipole molecule, but in the ground state, there's no dipole moment in the lab frame. So only by mixing the opposite parity state, I get effective dipole moment. And I can control it with the detuning of the dressing field. So that's already cool. I can induce in a controlled way a dipole. Up to like 1.3 dpi. And if you want to look at this in a classical picture, with this microwave field, we induce a rotating dipole. So basically, we set the dipole into rotation using the microwave. Okay, and these rotating dipoles now interact. And it turns out, as was pointed out on the theory side, and I think initially it's good to be true, but in the end it is true, when you have distressed molecules, they feel a repulsion in all 3 room directions, no matter how they meet. So that's a bit counterintuitive. If you use my classical picture, you have rotating dipoles. We said rotating dipoles that meet side by side. So when the rotating dipoles meet on the vertical axis, well, they obviously repel each other. But when they meet in the horizontal plane, it's not so clear. At one moment in time, they may be aligned like that, then they attract each other. Next moment, they may be like that, then they repel each other. So you need to think in a time average potential. And actually, it still turns out that the interaction is attractive. But as the molecules attract each other, the dipole-dipole interaction becomes strong enough at some point that other rotational substates get upmixed. And when you prepare the right dress state, they get upmixed in a way that the molecules realign and continue rotating side by side. With that, you get a repulsion in 3D. Sparman helped us to figure out the details for our specific molecule, for our sodium-cesium molecule on the theory end. And this is the interaction potential that we get for certain parameters. This is the collisional energy. This is the distance between 2 molecules. And the molecules approach, nothing happens. At some point, a repulsive ball comes at a distance of about 1,000 Bohr radius. So just to visualize that for you, our molecule has about 10 of 8 Bohr radii, and then there is a repulsive wall built around it that is 1,000 Bohr radii. So out of like a point particle, you make a big ball. It's not quite as extreme as a Rydberg blockade radius, but still something pretty. Okay, let's throw this on our molecules. So, let's first look at what happens to molecules when we don't do this. We hold a molecular ensemble in our trap and just wait. Without anything, the lifetime of the ensemble is just like 16 milliseconds. Now, when we throw on this microwave field, dressing field, we can extend the lifetime to a second. So we enhanced the lifetime by a factor of 50. So when we saw this, we were extremely pleased. It was at the time the biggest enhancement of a lifetime in a molecular sample. But our goal was to see if we can cool the molecules to BEC. And indeed, when we try to cool the molecules, evaporatively cool the molecules with this shielding, we would get to a phase-space density of like 0.1, just short of seeing a BEC. Well, that is because we actually don't suppress losses sufficiently enough. I told you before, we want to suppress by a factor of 100 to 1,000. So what's going on? In the end, from the theory point of view, using Theis' theory, we would have expected that we should get loss suppression sufficient to make a BEC. So what's going on? What limits the cooling performance? It turns out, when we look closely into our collisional, rest collisional potential, it's not completely flat when the molecules approach each other, but I told you when they meet in the horizontal plane, there's first an attraction before you get the repulsion. So there is actually a bit of a well here. And when the potential well is deep enough, you can have a bounce state in it. And when you have a bounce state, you have actually a potential loss channel that comes from three-body recombination. You can have two molecules go into the bounce state and the third one carrying away the excess energy. That was, of course, far from obvious before we did this, but it turned out that is a plausible explanation for observation of limiting performance of the microwave shielding. We modeled that in collaboration with Chris Green, and we find that the recombination rate into this bounce state aligns extremely well with our observed three-body loss rate. It's also a side note, is really saw an experiment that we moved from two-body losses, which you get when you don't have the shielding, to three-body losses, which you get when you have the shielding. Three-body losses then signifying this recombination. So basically, as soon as you understood this, we realized the name of the game is to get rid of this bounce state. Turns out, it seems there's no free lunch. When the bounce state is also actually the parameters where the shielding is the best. The two-body shielding is the best. So, how to resolve this problem? And the solution to this problem is really to just make a Bose-Einstein. So what have we done so far? We have prepared our molecular gas in a dipole trap, applying the sigma plus dressing field, and we get now this attractive potential. Now, we have other states that we can work with here as well. So let's think about adding another dressing field, a dressing field on this pi microwave position. So what do we do there? With the sigma field, we induce rotating dipoles, and the rotating dipoles, attract each other in the horizontal plane. Now, if we induce also vertically oscillating dipoles, and we try to think about what's happening is, well, if they meet side by side, they actually repel each other. So it seems there's a sign change. So there's a really, what is a minus sign in the case of sigma dressing becomes a plus sign in the case of pi dressing. So you see that the dipoles are really interacting in a complementary way. And that kind of led us intuitively to think, maybe we can combine two dressing fields and engineer a collisional potential that does away with this attractive potential. And lo and behold, if you actually do the precise calculation, there are parameters where this is possible, again, thanks to our collaborator Sebastian for figuring the details out. So again, here we show the energy versus the intermolecular distance. And for certain choice of parameters, we should be able to make an all-repulsive collisional potential, which is flat, 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 and then the barrier constant, completely repulsive. So this is put now on our molecular gas. So we have the molecules at microkelvin temperature in a dipole trap, two dressing fields switched on, and then we do an evaporative cooling sequence where we slowly lower the depths of our dipole trap. This is what we see. So here, this plot you need to read from the right to the left. Initially, we start at 700 nanokelvin with a sample of a few tens of thousands of molecules. And then we take snapshots at different times of evaporation. You see the temperature goes down, and well, the phase-space density goes up. Phase-space density is basically a measure for the ratio of the Brownian wavelengths over the interparticle space. So we get a BEC when this is 1. So this goes up much deeper than it used to be when we only use a single dressing field for shielding. And more importantly, it seems we can hit here phase space density of 1. Okay, so this is great. And it's a great point to look here at the actual molecular cloud and see what happens. So the last point that I showed you in this plot is actually a molecular cloud that is still very well fit by a Gaussian fit function. So this is still a thermal gas at a temperature of 40 nanokelvin. If we now cool further, we actually see that this profile changes and the peak grows out in the middle. And we can fit this with a bimodal distribution and get a condensate fraction of up to 60%. So that's the observation of the crossing of the phase transition. That was a great moment in the lab. Easy by now. And we can put these points onto our graph here. We see that we increase the phase space density by a factor of 1,000 in the molecular gas, and we cool it from 700 nanokelvin down to 6 nanokelvin. Definitely the coldest molecular gases ever produced. We fit the temperature by fitting the thermal wing. So for the experts, there's a couple of other considerations that we may want to keep in mind. So the typical density in our system is on the order of 10 to the 12 per cubic centimeter, which means that the particle spacing is close to a micrometer. And to make a BEC, we actually want to work in the limit of weak interactions. We want a weakly interacting Bose gas. So it matters what is the S-wave scattering length and what is the dipole length. We want them to be a lot smaller than the interparticle spacing. And indeed, this is what we have here. Although the S-wave scattering length is 1,500 Bohr radii, compared to the interparticle spacing of a micrometer, which corresponds to 20,000 Bohr radii, it's actually weakly interacting. And also the dipolar length is only 1,300 Bohr radii here. How did we achieve that? I told you before, we can get dipolar lengths of several micrometer. Well, that is also possible due to this combination of the dressing fields, where we actually make the long-range tail of the interactions flat. We're basically compensating attractive dipolar interactions with repulsive dipolar interaction of the sigma field with repulsive dipolar interaction of the pi field and vice versa. So with this combination of dressing fields, we can actually on purpose reduce the dipolar interactions to make a weakly interacting Bose gas that condenses, doesn't have notable contribution. We also can measure the lifetime in the BEC. We see a lifetime above a second, which was mind-blowing to us. At the time, we always struggled with millisecond lifetimes, and now we actually have losses that are suppressed by a factor of 10,000 compared to the unshielded case. So that is really was the key to make these. Okay, lots of excitement. By now we can actually got quite a bit better in this microwave shielding. So if you squint your eyes, you see that the system sizes of the BECs that we make are around 1,000 or actually just a few hundred molecules in the pure BECs. By now we can make BECs with 2,000 molecules, so we have increased the number of and the evaporation efficiency is 3, so we gain 3 orders of magnitude of phase space density when throwing away a factor of 10 of molecules. So there's a really good efficiency, like we get the level of atomic evaporation now. And this 2,000 molecule BECs now is quite nice because it allows us to do single shot imaging. And finally, we can do this. Okay. That's right. Nice 3 pictures across the BEC transition. Okay, with that, let's get into exploring the BEC. So one important question is, you made a BEC in the weakly interacting regime. So what happens actually to the molecular gas when you make the tension stronger? And there is a very straightforward way to do that. To make the BEC, we balance the dressing of the sigma and the pi field in a way that on purpose the long-range interactions are dialed down to a very low value. But we can imbalance the dressing field. We can basically increase or increase the pi radio frequency, and with that we can reduce the impact or enhance the impact of the dipolar interactions. So note now here we start giving names to the two types of dipolar interactions that are induced with the pi field and the sigma field. The pi dressing dress dipole we call dipolar interactions, and the sigma plus dress dipoles interact in an anti-dipolar way. We call this anti-dipolar because of the sign shift. And by tuning this balance, we can really tune the dipolar lengths from zero, close to zero, where we make the BEC, to like, very strongly anti-dipolar with dipolar lengths of the 20 minus 20,000, or very strongly dipolar with similar dipolar lengths in the other direction. So, but important question. So that is sort of on the single molecule level what can happen, but what happens to collisional losses? That's something we studied. So we measure the two-body loss strength in our samples, and nicely distinguish in our measurements 2- and 3-body losses. We always find that two-body losses follow Weiss's theory. So they are very strongly suppressed, well below 10 to the minus 13 cubic centimeter per second. So we focus our measurements on the 3-body losses. When we only do dressing with a sigma field, we get fairly high 3-body losses, as shown here. When we introduce the pi field at the BEC point, when we make the BEC, we get a very strong suppression of 3-body losses by a factor of 1,000. Now the question is, what happens in between? Amazingly, we find that 3-body losses and 2-body losses, they extremely suppress in a fairly broad tuning window. Before they come back up because the collisional potential has a bounce state. And you also see here, there's a gray shaded area. That's actually our detection limit. The detection limit is set by the finite 1-body lifetime of the molecule. So we basically suppress 2- and 3-body loss below our detection limit. Something quite cool, something that's even hard to know in atoms. In terms of what the tuning window means, is where the losses are suppressed in terms of dipolar interactions, is we can tune the dipole length from 0 to 20,000 over radio. So that is some, in some sense, you can think of it as like, the Fechner resonance for dipolar interactions. You can tune from 0 to a large finite value in terms of dipolar range. That we can use to try to understand, what is sort of the strengths of interactions we can induce in our system. And one thing that we can do is from the loss measurements or loss rates that we measure, we can extract what kind of densities can allow to have a lifetime of the sample to be larger than 100 milliseconds. It turns out in this window of very strong loss suppression, we should be able to get lifetimes larger than 100 milliseconds with molecular samples at a density of 10 to the 15 cubic centimeters. And if you use this density and calculate then the corresponding ratio of dipolar energy to kinetic energy, which is to measure for the interaction strength, you see that you should be able to tune from 0 to roughly, just below 7. So you have continuous tuning of the interaction strengths from very weakly interacting to very strongly interacting. That's exactly what we want. So that's sort of, all measurements done with a thermal gas. So, it will be interesting to throw this onto a degenerate. So what happens when we increase the interaction strength using this method on a BEC? So as I just told you, you can use interactions between the molecules by imbalancing the dressing field, the pi and the sigma dressing field, and get dipolar, anti-dipolar interactions. But it turns out there's another method. We can also tune using our nice cloverleaf antenna. We can tune the ellipticity of the microwave field, and with that we break the axial symmetry of our interacting molecules. And it turns out we can introduce a new form of dipolar interactions, a form of dipolar interactions which has an azimuthal mechanics, which has a new type of anisotropy, corresponds to spherical harmonic Y22. So it has no interactions on the vertical plane and attraction in one axis in plane and repulsion in the other axis. There's a very interesting new type of dipolar interactions, and this is what we throw on our BEC. And by tuning the ellipticity of our microwave field, we can tune the strength of this interaction. We can tune the AD the dipolar lengths. And one thing we can observe is that, we see that it's produced in a round track, and it's initially nice and round. It's like, squeezed and stretched in one direction or the other direction, depending on which direction we apply the electricity. So that's the observation of electrostriction in a dipolar molecular BEC. And also, change the angle of the electricity very continuously. The antenna allows to do this. We can kind of, think and hope that maybe we can use this to set our cloud interpretation, which could be interesting to draw superfluid properties. But this is closely related to very interesting work on evaporatively and magnetic atoms. So let's also look what happens, to the BEC when we are increasing the dipolar interaction strengths. So what we look here is at a BEC that is released from the trap, and then we look at different snapshots at different time of flights. And then we see, a BEC with a small dipolar interaction, close to zero, expands like a BEC. Here we cannot so good yet to make it round, now we're better at that. And when we increase the interactions in one direction, we see, well, the expansion behavior changes quite dramatically. BEC doesn't expand anymore. Since we see a self-bound droplet state, an interaction of minus 10,000 Kelvin. And if we go in the other direction, we see something even more spectacular happening. We see the BECs breaking up into separate pockets, and also these pockets, these droplets don't expand anymore. So that looks like a array of self-bound droplets. That's related to what has been done in magnetic atoms in certain regimes, but actually with the interactions now we go quite beyond the regimes that can be accessed as magnetic atoms, and we get into a regime where it's not clear anymore whether you can describe the physics with the extended Ross-Pedayevsky equation that has been very successful in magnetic atoms. We also, it's nice to highlight, we can actually tune the speed at which we change interactions extremely well, because everything is microwave controlled. Microwaves we can control on the sub-microsecond scale or even faster. And we can look at what happens when we change the speed at which we go from weakly dipolarization to strongly dipolarization. We can change the ramp speed at which the interactions come on. We go very slow, 400 milliseconds change. We see a nice, ordered quantity array of droplets, and we go much faster. We see the, mesmerizing pictures of, excited droplet array arrangements. There's a whole playground now opening up things to start. So basically, with this, let me give you a bit of a brief outline. With what we observe, I think we can start thinking of the molecular gas as a new modality for quantum simulation. In many ways, we have a similar level of control now over the molecules as we have for just to highlight a few things, I told you already about the interaction tunability that we achieve with the microwave fields. We tune really the collisional potential of the molecules. That includes tuning of the long-range dipolar interactions. It includes the tuning of the hard sphere radius, so we really make hard sphere bosons here, and the tuning of the bound state in this collisional potential, which actually is the tuning knob for the S-wave scattering. It's a very versatile way to directly tune collisional properties in our quantum system. More visually is you can make a system where the interaction range is fairly short in the ensemble. And then, abruptly, you can make the interaction range larger than the particle space. So that is, really opening new ways for French protocols, for blockade engineering. In some sense, also, quantum simulation of quantum collisions here, because we have really this comprehensive control over the collisional potential. Since it seems to be very interesting, we're going to continue studying our BECs in 3D. A lot of interesting predictions have been made. We are excited to also put the system into 2D. And already for a while, phase diagrams have been proposed for weakly dipolar 2D dipoles in 2D. Superfluid is predicted, but when the interaction gets strong enough, this should self-organize into a crystal. And we have some hope with the strong dipolar interactions of NACS that this can be done in a way that we have like a micrometer interparticle spacing. We can actually hope to see this crystal form and melt, for example, when we increase the temperature. Also, obviously, it will be exciting to put the molecules into a lattice. It has been a huge challenge so far to load lattices molecules into lattices with high filling fraction, but coming from a BEC, I think there's a good chance to reach close to unity filling, or to actually study standard Harvard models where you expect like solid non-insulator fractional filling. Also, of course, with a unit fill lattice, it would be interesting to study using the dipoles still in that space. Okay, with that, I'll give you just a 3-minute overview of what's happening in our second experiment that John mentioned, the atomic tweezer array of strontium.
Oh, you're giving 2 back-to-back talks.
No, I'm keeping it.
No, he's got another hour. Nobody has anywhere to go, right? I got it. 3.
Yeah, I'll keep it.
Yeah, 3 minutes is good, isn't it?
Yeah.
I ate 5 of your minutes, so.
Yeah, that sounds. So the one motivation of this setup is to actually get into a regime where we can study super and sub radiance. That's inspired with a lot of discussions with our friend and colleague Garcia at Columbia, where when we are able to bring atoms in an array close enough together to each other, we can hope to see cooperative emission effects in free space without the aid of a cavity, for example. And here the key goal is to bring atoms close enough to each other that they're closer than the emission wavelength as well. But if we want to do that with a tweezer array, typical spacings will be on the micrometer. So how can we get into the sub-wavelength regime? Well, we use strontium, and strontium has a very interesting 2.9 micrometer bit infrared transition, and that is the strategy we pursue. So that's the experiment itself. As John mentioned already, we have driven forward a new way of making tweezer arrays using transmissive metasurfaces, holographic metasurfaces that allow us to make the tweezer arrays in which we trap atoms. One property to highlight is it's very power resilient, so you can shine a lot of power on these. Also turns out we can make very high quantity arrays of any shapes and forms. So it's basically like an SLM, but as I will show you in a second, with a couple of advantages compared to an SLM. Can make very dense arrays with a micrometer spacing between the traps, also large arrays. That's not so great yet, but we actually have better images of 1,000 trap arrays. Right. You can do single atom trapping in these arrays and see if I can get it better than 99%. Just highlighting a few special properties of the metasurfaces to make tweezer arrays. So basically, metasurface is a ultra high resolution face mask, similar to SLM, but with the important distinction that the pixel size is basically 100 times smaller than SLM. With that, we can emulate very steep phase gradients, and we effectively get a device with a very high effective NK that can directly focus the beams into the tweezer array at the size where we can actually trap the atoms. That's for SLMs, you always need magnification of pixels. And the small pixel size also allows us to have a lot of pixels on the device, like hundreds of billions of pixels. And if you start looking into the details of it, that matters because you need a lot of pixels to make a lot of traps. In our simulation, we find that you need about 300 pixels to make one high quality trap in a tweezer array. That means when you have an SLM with 1 billion pixels, you are limited to a few thousand high quality traps. With the metasurface, we should be able to get this really up a factor of 100 or more. Also, just briefly mentioning progress on this 2.9 micrometer transition. So we have broken now this transition with atoms in the array, not an ordered array yet. This is the average picture, but we see this transition has alignments of 60 kilohertz. We see alignments in that order on tweezer trapped atoms. So that is now ready for the next steps. We're currently working on sorting. We've put that off to the very last minute. And but as soon as we can sort of get unity filled consolidated arrays, we should be in a very exciting stage. Okay. Also, we have collaborations with the Brookhaven National Labs and quantum networks. Actually, we'll have a quantum network connection that goes live from Columbia to Brookhaven just in a few weeks. So we're very excited about that. You can ask me about more details of what's going on there. So with that, I'll summarize, focusing on the molecules. As I showed you, we made a PC of molecules. I'll focus on a couple of take-home messages. I think we can say now we have a similar level of control over the molecules as we have for atoms. We have real-time control over collisions and interactions in the molecules. And with this droplet formation, I mean, we are seeing the onset of studying a new type of dipolar, strongly dipolar quantum. With that, I'll thank my group, the NACS team, Dr. Ian Stevenson. We moved to Virginia for a faculty position. Former student Niccolo Vigali was really a driver of the PC experiment. Also Claire Warner, A.D. Lam, earlier graduates, new generation, Silver Chang, Wei Jin Yuan, and Tana Okwa and Boris Bulatovic from the next generation, as well as Asaf Tobrachi. And for tweezer, we have postdoc Bojan Seo and a senior grad student Aaron Holman, extreme driving of course. Thank you to collaborators, funding agencies. Apply to Columbia if you are interested in PhD position or postdoc. And thanks so much. All right, any questions?
One of the slides, when you got the slide where you showed not free the contrast, I think they do 70 years.
Yeah, so this is the loss rate coefficient. So we need to multiply by, for the super body loss rate, you get the loss rate, multiply by the density squared. Then you get the actual rate. So, and from that, you already see, yeah, basically, anyway, so this is 10 to the minus 25 level. So, at a 10 to the 20, the 12th density, you get like 10 seconds, which is our detection. That's why this is where the detection.
So in this like kind of flight images that you're showing where you have like the separating cloud.
Yeah.
Do you understand what like distinguishes each cloud? Like is one cloud have like a different label compared to the other one?
Yeah, no, this is a very interesting question that basically points to trying to understand whether this is actually phase coherence setting, for example. I mean, that's something we're really excited to study. So that's a question that was also addressed in magnetic atoms in a series of experiments, trying to figure out, can this be a supersolid? Can this be actually a localized superfluid across the different droplets? And that's something we are working on. Basically, we would like to figure out how we can interfere this. And one thing that comes in handy is it's still not so easy as it sounds, but one thing that comes in handy is you can switch the interaction arbitrarily fast. Go from this strongly interacting case, slam the dipolar interactions down to 0, go here basically, and then we should expect that this is expanding and perhaps these clouds are overlapping. That's the dream. Not as simple as this.
I actually have one.
Yes.
Which is, you told me that you were gonna add multiple microwave dressing fields. My immediate response would have been all hell is going to reduce. So is there a way I should understand that we actually can do this and it works really well and you can see?
Yeah. So thanks so much for this question. So actually we acknowledge data. And basically what happened is I was at the CUA for a talk, and then I was randomly talking to Data about all kinds of things, cesium and all this. Last 10 seconds we spoke about microwaves. And I said, like, well, we have this issue with the microwaves. We want to combine two fields, but they need to be super orthogonal on each other. And we need to control the polarization. So it seems pretty hard. And then we said, like, okay, you just add compensation fields. And with microwaves, that works. We do that, whatever, for our turbulence. And then I said, okay, thanks. Okay, then come to the lab. And just the fact that he said it, it's obvious that it can work. But the fact that he said it was crucial for us to actually do it. And then we add, actually, I kind of sweep that under the rug in the explanation, but there is a certain alternative. Corrects for the alignment of the microwave field. What matters a lot is that the linear field stays perfectly perpendicular on the plane of the circular field. Otherwise, you mess up the compensation x, essentially it goes. So there is from the bottom another compensation antenna that tilts this field to be orthogonal.
And do you measure this with the atoms or you measure it ex situ?
So we have, if you go to the methods of our paper, there's like extensive spectroscopic approach to measure all tilts of the microwave fields. So basically, spectroscopically, we measure the tilts to a crazy level, and then we give compensation fields. Now we figured out a way to even give compensation fields without this extra antenna by feeding extra fields to the cloverleaf antenna that correct for the tilt of this guy, and works beautifully.
And so should I think of some of this compensation to be compensating for like reflections off of things too, or those end up not mattering?
So in some sense we are a little bit lucky. So we are in the still chamber, but thank God the viewport on top is large enough that the antenna just fits in, and there is not too much metal in the way for the circular. When we basically put like all powers in the cloverleaf antenna and for each loop the same at 90-degree phase shift, we are already pretty close to what we need. And then we ask the molecules what we need to do to correct. But we are not so far away. For the linear, it's much harder. Ironically, we have an antenna that's like 20 centimeters away, needs to go through some metal tube essentially. We can rotate this antenna at any angle. The polarization that comes at the molecule is always the same. It's purely determined by boundary conditions. So that is why with an additional antenna that is again going through the nice loop port, we can compensate it. So you want one antenna that does reliable things, then you can correct antennas that do not unreliable things. It's a little bit of that, but that we built the chamber. Of course, I thought about this as such. It didn't at first.
Right. So we have one more question we can do it, otherwise I think we should probably just thank Sebastian.